Alrighty then. Where did summer go?
You working hard?
Last thing I remember was that it was June.
I know.
But we had a great summer up on the hill. I mean, my report, you know about it, is in the Sky News. And just a reminder that we have our AGM coming up on Sunday, November 22nd. I've got a rough draft of the evening's program ready to go, including the menu. As soon as we approve that, we'll get it online, and then we'll start taking orders for that evening. So what you need to do is I'll send out an email saying it's online. You know, look at it, then you'll be contacting Nelson either by phone or email and let them know who's coming, if you're bringing a spouse or a friend or whatever, and what you like for your entrees and starters and stuff, and we'll get going and get the restaurant up to speed on that. Also, there's elections coming up too, so on that same night. So, I mean, whether you're an incumbent or just a member in good standing who might like to be on council, let us know.
As long as Harper doesn't win.
Exactly.
Guaranteed Harper. He's not running here.
It sounds like we will be needing a new secretary. It sounds like Malcolm is stepping down from doing Sky News, so we'll need a Sky News editor. And any other position, as long as you're never good standing, let us know if you want to run for it, and we'll put you on the slate for the elections as well. We'll go straight to Bruce.
Currently, our member account is standing at $12,024, which is kind of nice. Our gaming account is at $1,120. And on the actual public outreach end of it, I'm running an event, which I hope as many of you with telescopes can be at, and everyone else who doesn't have telescopes as well. September 18th, RASC will at Point. Be about 8:30 p.m. once it gets dark enough for seeing anything. And then October 16th will be the one after that. So they'll be on a Friday. It's near around the quarter-ish, you know, last quarter kind of moon. So I'm not going to time these on any new moons to make everyone mad at me. So. And then on Mount Tolmie on September 27th, I plan to be up there for the lunar eclipse. Anyone's free to join me up there with their telescopes, and we'll all be up there being mobbed by teenagers from UVic probably. So it'll be pretty fun. And that's what's going on right now.
Thanks, Bruce. Joy.
The June council and general meeting minutes have been posted, thanks to Joe. So anybody who wants to take a look at them can read them online.
Good, thanks. Joe, anything from BP2?
No, nothing from BP2. The meetings are all planned to the end of December, and as far as speakers are concerned, anyway. And that's about it.
I think we actually don't plan it out till the end of March, because I managed to say 3 people.
We have people on the possibilities list, but nobody's actually said they're going to do this.
And second vice president, or first vice president, is one of the positions that will be open in November up for election.
That's right. I'm just filling the role, and I made it clear I won't be filling it after December. So.
I much appreciated this last year too, but thank you for that. But yeah, definitely we'll need a first vice president as well.
So if anyone's interested, let me know at coffee and we can talk.
Chris.
Okay, we have 216 members currently. There are 2 people who are in the grace period whose membership has actually expired and haven't renewed yet. September 30th is a fairly major membership expiry date for the club, so there's a few people going to show up on the list if they don't renew this month. Astronomy Cafe will be resuming on Monday at 7:30 at the usual location in Fairfield. And I have an outreach event on, I think it's the 26th of September at the Fall Fairfield Harvest Fete. They asked us to put out a table and connect to the public, and we'll do some solar viewing if it works out. If you're interested, let me know, and I'll be probably contacting some people as well.
Good thing. Are there any new people here tonight? You don't even have a clue what we're talking about, right? If you want to know what some of these events are all about, just see us as soon as we wrap up the meeting. We always meet upstairs in the Astronomy Lounge on the 4th floor of the Elliott Building afterwards for coffee and cookies. If you want to come up then, you're welcome to join us. If you don't, if you want to find out what this is all about, just come down and talk to one of us before we head out there, and we'll let you know what we're talking about. Some of us actually know. Welcome, Sky News.
Yeah, Sky News is in front for those that pick them up. And for anybody that's here visiting tonight, you can grab one if there are two.
Is there more than one?
Pardon?
Is there more than one?
Yes, there is. Other than that, I will be continuing with the newsletter for the next 3 months. And if anybody wants some information about what it's involved and how if they want to participate in it, that would be great. Other than that, it's pretty simple. I use a Mac and it's pretty straightforward. Thank you.
Sky News is available for download as well from the website. Just click on News.
Thanks, Malcolm. Let's go through this really quick. The start party, well, those of you that were there, that was pretty neat. I mean, we had, for once, no wind, almost no dew. We had just a little bit of haze the second night. Great crowds, great prizes. I mean, it went really, really well. So thanks to everybody that helped put it on and physical stuff like setting up chairs and all that, and taking it down at the end, and people showed up. As visitors, it was actually a really good one this year. There's some discussion about when to have it next year. I think we probably didn't get as many people as we normally do because of the first quarter moon. I think some astro imagers didn't show up. I know there's a few people from the mainland who come. I don't know why, but possibly because it wasn't as dark as it could be for them. You might be thinking about doing it in September next year, during the new moon. We can't do it in the new moon in August because the Cowichan Valley people have the next 3 or 4 of those taken. So we may think about doing it in September. The nights are longer, it's darker.
Moisture.
But there could be more moisture and it's definitely colder. So. What's that?
Short Canadians.
Some of us are old. So we'll let you know within a year to figure that out, but it might be that we try again in September. Public outreach, Sid.
Thank you, Madam President. Thank you. I have some good news and bad news for you guys. Would you like to hear the bad news first?
Yeah.
The good news is this is my last report.
That's not the good news.
I expected that you don't have to listen to me all the time, hounding you, say, I need you, I need you. Anyway, that's the bad news. Sorry, that's the good news. The bad news is you can't get rid of me yet.
That's the good news.
Reporting with a school telescope program. So I will be asking you to come and help at the school's night sky viewing, which is coming on September 24th, Thursday, at St. Margaret School. Now, this is a test for you. I'm not going to ask you to volunteer. I would like you to come to me, say, I will help, I will help, I will help. Let's see how it will go. The last big public outreach programs we had was Hemisphere. It was quite better than last year as far as the weather was concerned, because last year we had a stream running where the path is. This year we did not have any stream running, but we did not have as many Galileo moments as we had last year. Last year we had 1,446. The peak, one-day peak was 616. The peak for this year was 542 this week, but that's all right. This is better than nothing. So this year Galileo moment at Senate Square was 1317 compared to 1446. However, total Galileo moments for this year as of yesterday, 10,500. This is because of you guys volunteering. I kept hounding on you, but you were gracious enough to say, yes, I will come, I will come, I will help. Thank you. So, another bits of information you would be very interested to know, there's 57 of us, of you, who came to help. 57 out of whatever. And the number of volunteer hours, 1454. So that's not bad. We were out, almost 70 times through the whole year, out doing something. And at the Senate Fair, we had a very exciting event called Team Telescope Draw, and there were 109 entries. Out of that, one girl, I don't know how old is she, 12 years old, she hasn't got the telescope yet, but she is the proud winner of a team telescope. And if you have any questions, want to know more about public outreach program, please come and I will teach you how to do it. It's a switch, no problem. Thank you.
Thanks, Ed. Okay, Lori.
So we have one more night to go on this coming Saturday for the Diego Summer Saturdays, and we're expecting a huge crowd because Bruce sat there and told 1,372 people at the Spanish Fair that they could come up. So we're expecting a big crowd. We told everybody to come early. I will be putting out my list for tomorrow. So if anybody wants to let me know tonight that they are definitely going to be there for Saturday, that would be great. And then I don't have to email everybody else out for how many people will be coming. Hands up, how many people believe that they are coming on Saturday night for helping? Yes. Okay, that's great. Good. I'll just, so if you can just drop me a little, just yell at me and poke my shoulder and tell me to put down my name. Make sure.
And I was going to say, can we get an early gate time?
An early gate time?
Yeah, so because if we're going to be so busy,
Well, I'll be there.
for us, I mean.
For you guys, I will be there. I'll be there at 6. We'll be able to get you in early, and in fact, I think we have the Gemini feed is going to be coming from the Gemini telescope in Hawaii. We have Mary Beth Lachek coming, who is the public outreach coordinator for the CFHT telescope, and we have a speaker from the university who is also going to be speaking on the 30-meter telescope. So this is Hawaii night, and everybody is to wear Hawaiian shirts. And wouldn't it be nice to have my ties? Anyway, so it's a real kind of Hawaiian night, and so what we're hoping to do is, because we've got such a packed program in the auditorium, we're actually going to ask, probably actually get the public up a little bit early, like somewhere between 7:15 and 7:30. We know that there's going to be a lineup at 6:30 out there, and so I think we'd like to get the people up in there so that we can get the program started right at 7:30, because we've just got such a full program going on. So please, if you are going to come, Sherry, you've still got that printout that we could send for putting something in your car. You still got that?
I'll send it around again.
Send it around again. So just plug in your car, RASC volunteer. You can print it off, put it right in your car, I will have a list of all the volunteers, the people at the gate will have that, and they'll be able to let you in. And then just kind of go around on the left of everybody to be able to get in. So it should be wild and crazy, and hopefully everything will be all right. Yes, Jordan.
Following up Chris, if the public is coming up to write at the, earlier than before, those who are setting up telescopes really need to have more time.
Yeah, well, I mean, you guys can come in, I'll
At 6?
be there, I'll be there at 6 if you guys want to be here, started to come in by 6:30, like, please do, yeah.
Well, thank you.
We'll be there ready to let you in. Okay, if you want to, and we just know that's going to be there. So the only other thing that I would like to just draw your attention to is that that we have in the past couple of months incorporated the Friends of the DAO Society. So we are now a legitimate entity. And it took a little while, it took a couple of years to get that going, but we are there. We are doing a crowdfunding campaign right now. The society is trying to, basically our mandate will be to open up the center of the universe again for public programming, particularly the school program during the year. And to get the public programming back up again for fully more on Saturday nights. And that's going to take some money to get some part-time staff to be in there, because we already putting in hundreds of hours of our own time for this. There's no way that we can start to also ask to also do school programs all during the year and everything like that. So we want that's what that's for. And so we are having a crowdfunding campaign and a membership campaign. And if anybody is interested in becoming a member, it's $10 single and $15 for a family. And we would love your support. We would love everybody in the RASC to be also hopefully being a member of the Friends Society, and so that we can then go out. Now we're putting in a promo science grant. Some of you will know all about that kind of thing. We're trying to put in a promo science grant that is due next week. And we don't know, whether we'll be successful or not, but that's what we're trying to do right now. So if there's any questions, come and see me, and certainly the group will be up on Saturday night if you'd like to put in donations there, or I can also take that. Okay, I think that's it.
Okay, thanks, Lori. Joe, website.
It's running. Sky News is up there. Thank you.
Okay, stuff now.
I'll add a little bit more to the website. Some analytics from July 1st to August 31st. We had 12,000 unique page views across 5,000-ish visitors, uniques. Top popular page was the homepage, obviously, but following that was the observatory and the DAO star parties with about 1,600 hits each. And those were also some of the top search terms, talking about the DAO star parties. Other than that, it was a pretty quiet summer on the tech front. I haven't really gotten up there to do a lot of maintenance or anything, but it's still there.
It seems to be working okay, so the new flooring and the dehumidifier seem to be working okay.
Yeah, the water issue is a non-issue anymore. So.
Good, yeah, good work. All right, thanks, Matt. The only other thing I have to add, actually, I forgot, is we have 3 nights this coming quarter on the 32-inch telescope you did here. It'll be the second Friday of each month, October, November, and December. So for those of you who don't know what that's about, we meet down here in the lobby and we get to use the 32-inch telescope on the top floor here for the entire night. Last I heard, it's not a photographic telescope yet because there was still some problem with the diagonal mirror in it not being completely plain. Some sort of aberration, so we can't really use our cameras, but we can use it for visual observing. So all the neat stuff in the fall, Scott will get to look at. So I'll be sending an email. It'll be myself, John, and Chris running the program, and it's a cool telescope. It runs just the same as our VCO telescope on the Sky 6. It's fun to use. It's a beautiful machine, and it gives great images, even though we're in the city with all this light pollution. Visually, it's still a really neat telescope to use. So the other thing actually is a couple people over the summer have mentioned that maybe we're a little bit intimidating with all the stuff that we have, like our own observatory with the fully computerized telescope and the great big Dobsonians that are hiding in the shed next to it and using this telescope here. Don't be afraid, it's actually a lot of fun. So if you're sort of kind of a bit nervous about this being really, intimidating or really, super high tech and you're never gonna, fit in, just come. I mean, just come. It's so much fun. You don't necessarily have to operate this stuff, but you get to look through it. And when you're looking through a 3D telescope, it's just like, wow, this is so much fun. So, I mean, when we put these notices out, don't be afraid just to come up and see. And if you have your own telescope, especially when we're up at the VCO, our own observatory on the Friday or Saturday nights, if you have a telescope, bring it. We'll show you how to use it. I mean, if you have one sitting at home, you just want to learn how to use one. We've got, small ones up there that you can haul out and use. We'll show you how to use it. Bring your own. I mean, I really want to make this fun for everybody, not just those of us who've been doing it for decades and decades. But I mean, people are just starting or just kind of learning about it. Just come on out. This is so much fun. And I promise we won't just overwhelm you with techie stuff. We'll actually get to let you look at the stars and neat stuff. So don't be afraid. Just come on out. National issues, Lori.
So I was at the national meeting, the AGM, along with Chris, and along with Chris, and Alex. Is Alex here? Alex is not here. So we had quite a Victoria group at the in Halifax, which was awesome. And we had a very good meeting. And of course, if you're not, there's Alex right there. You just came in right now. The most important thing that happened, one of the most important things is that the RASC National now owns the Sky News magazine. So the people who had owned that and were running that magazine, the Sky News magazine, that is the one in Canada, they wanted to sell that, and so the RASC was given kind of first rights. Is that right, Chris? First kick at the can, yes. And they accepted that. So we are now the owners. Not necessarily we're not going to be actually writing all the stuff. They're going to keep a lot of the people that worked on the magazine. And it will be, I believe that the editorship will be turned over, is it Gary Ceramic? Or not yet, that we don't really go on that, I shouldn't have said it. Whoops. We'll keep it in there, that's right. Okay, anyway, you'll deny it, okay. But lots of the people that worked on it are going to continue. The Sky News magazine is a very nice magazine for Canadian astronomy, and we don't want to do a lot of changing. We don't want to wreck what's good and what's already working. So that won't happen. And the money that was used to buy that was already in funds and accounts. So it wasn't as though it was being taken out and we're going to ask you for another $8 per person, to be a national member. It was already in there and it was taken out of so there's lots of little bits that happened there. Chris, is there anything else that was totally major that should be? I mean, there's all kinds of little bits, but I'm not sure that right now.
That's the important thing.
I think that's the important thing that was there. If anybody have any questions or anything, you can ask me. And of course, online, they did do a new website. There is a new website, and a lot of work was done behind the scenes on that. Go there, you can go and check out everything that's online. It's online. All right, thank you.
Thanks. Anybody have anything to add, to ask?
I have something to add. I want to elaborate just a tiny bit on what Sherry said about our elections coming up. As the past president, I'm charged with the responsibility of putting together a slate of candidates for your perusal at the AGM, prior to the AGM actually. And this particular year presents some pretty serious difficulties occasioned by the departure of the first vice president at the beginning of this last year, Charles, that went to Montreal. And we're losing Joy, our secretary, who won't be here for the second half of what would have been firstly a 2-year term. So we have two important positions to fill, and the position of first vice president is particularly important because it is the first vice president that traditionally after a 2-year term has become the president. So we are left with having to fill the slot of first vice president and the slot of secretary and the slot of Sky News editor, and to try and make that coincide with some sort of reasonable procession of people through these offices. So I guess what I'm trying to say is that we need people that have not been involved in being on council or have not held these particular positions. We need people to come forward that may be a little uncomfortable in doing it. None of these things are particularly difficult to do. Probably the most onerous as far as day-to-day work is being the secretary. And it is one of the most important. So if you've been on council and haven't held a major position, or you've been a chair of a group like the technical group or the outreach group, please consider, or please at least give me a call and we can talk about what some of these things entail. Because it's incredibly important to this club that we keep this leadership thing going. We've had a very nice procession for literally the entire time I've been here. We've had what I view to be highly competent leadership, and I hate to see that just kind of further away because people's jobs and whatever take them elsewhere, and then we're left kind of this rift. To plug into these positions. So if you have any interest at all in doing any of this stuff, anything, any kind of vice president, anything like that, give me a call and we can talk about it, and we can find a spot for you to be nominated and presented at the AGM. But my email address on the site obviously is pastpresident at pastpresident, whatever it is. So please get in touch with me if you have even the vaguest interest in doing this.
Okay, thanks, Nelson. Just so everybody knows, all our contact information is on the website under About Us. Just click on that, and our names and email addresses and mostly home numbers are on there too.
Yes, actually it is kind of hard to find. It's where it says About Us, and then there's a list of things. The list of people is not included in the list of things. It's actually included in clicking on About Us and not on the menu item.
Yeah, so if you hover something, a drop-down menu.
Yeah, don't go there.
So don't hover, just click.
Just click.
And then everything comes up. So, anything else from anyone? We're good? All right, now I will turn it over to Joe, and he will introduce our guest speaker for the evening.
Yeah. Our speaker this evening is John Willis, who is a UVic prof, astronomy and physics, and he promises he has a really strong voice, so he's not going to be using a microphone. We'll see how that goes. The mic's right here. The last time John spoke to us actually was a heck of a long time ago, in 2004. We invited him to our AGM, and he and his wife Sarah came and we had a good time. So it's about time to hear from John again. That he's written a book, and you can see the title up there of his talk tonight. All his facts and figures are on the website if you want, but I basically would like to say that he's been a prof at UVic for quite a long time now, and I think he's retiring, and a competitor has come back from Okanagan. How did you know that? Oh, well, word spreads. And you did actually mention it to me. Oh, so there you go. Without further ado, John Moss.
Thank you very much. Good evening, everyone. Thank you for the invite to come and talk to you again. So, the search for alien life in the universe. So it's a pretty broad topic, and we'll see if I can do at least parts of it some justice tonight. I also should say that when Joe asked me, I was keenly aware that I'd be speaking to an audience of very enthusiastic observers. So I've tried, where possible, to pick out perhaps some challenging night sky objects, but ones that should be accessible to you. So I'll be offering some tips for how to find them through the talk. Are my volume levels okay? A little bit high. Well, I might put this on because I started lecturing today. So my first course was today at 9:30. So you start to flag a little bit come the evening. So I just keep talking, you're going to pick me up. Let's see what we can do. Keep talking, we get anything?
Yeah.
Oh, we're getting something, yeah, that's good. Okay, if you want a little bit more, we're good. A little more, okay. Let's go for 100%. There we go. We can't go to 11, we're stuck at 10 here, so let's see how this goes. So, the reason I'm talking to you about the search for alien life as the universe is only because I give a course on it at UVic. And the history is, the only reason I'm giving a course on it is because I think it's cool. It's just fundamentally exciting stuff. I don't actually do research on it. I'm hoping to in the future to get involved. My main research topic is what we might call very deep field cosmology, some of the most distant objects in the universe. But the search for life in the universe fascinates me. And so one of the great things about UVic is you can still make trouble and create new courses and get the opportunity to teach them. So I've been doing that for about the last 4 years. And then I got a sabbatical. And as far as judging by the questions most people have asked me about what you do on a sabbatical, their idea is that you sit in an office and you smoke a pipe for a year. Right? That seems to be what they think I was up to. And I told them, no, I basically sat in an office and I typed for a year. I never intended to write a book. I just thought at the start of the sabbatical, well, maybe I'll write a chapter and I'll see what happens. And I kind of enjoyed writing the chapter, actually. I enjoyed it way more than doing research. Writing about other people's research is way easier than doing your own, it turns out. And so I got carried away. And then I kind of found a publisher and the book's going to come out, etc. Now, I'm very embarrassed about the whole book thing because when Joe asked me back in the spring, I kind of finished writing the main text and I sent it to the publisher and I thought, great, it'll be out in a couple of weeks. And that's not how it works. Well, maybe if you're George Martin and you finish the latest installment of Game of Thrones, they'll kind of speed things up a bit for you. But, there's a few hoops to go through, etc. It turns out it's probably going to be out in spring next year. But the talk I'm going to give you this evening has kind of grown from that book and been inspired by it. So that's the kind of the background to what I'm going to talk about. I mean, the big overview here is, do aliens exist? Okay. It's actually the first line of the book, and I give you the answer in the second line. Yes. All right. Undoubtedly, aliens exist somewhere in the universe. Now, my only reason for saying that with such certainty is largely if you like, theoretical. The universe, as you all know, is a big place, right? Possibly, quite probably, bigger than the observable universe that we can see, simply because of the finite speed of light. Okay? So it may well be that the simplest universe we live in is one that's infinite in size. And as you all know, if you roll a dice an infinite number of times, it doesn't matter how small the probability of getting a particular number is, you're going to get your lucky number sooner or later. Now that's one answer. It's a very glib answer. It's also, from my perspective, completely unsatisfying because it tells us nothing about alien life. And so the next thing you have to ask is there any scientific evidence for alien life beyond Earth? And the answer there is just as resounding a no. Okay? And the challenge of astrobiology is actually to go out and obtain that evidence. This is just showing us the pitfalls of what you might call a human-centered view of alien life. Okay? It's a health warning for budding astrobiologists not to be too guided by preconceptions about what life may be like. Now, there's also a practical point of view. You've got to start research somewhere. So we start our search on Earth, trying to understand life on Earth. And then from what we've understood about life on Earth, we try and reasonably extrapolate to how life similar to Earth life and adapted to the conditions we see perhaps in the solar system or in exoplanets beyond the solar system. Now, let me just give you a quick run through of the book, because I'm not going to do the whole book. The book basically picks out what I think are some of the 5 most plausible scenarios for encountering alien life. So the quick 1-minute summary is, there's a chapter on Mars. Okay? I'm not saying probable for finding life, I'm saying plausible. Now we're spending an awful lot of effort, an awful lot of scientific investment exploring Mars at the moment. Another candidate this is Europa, is a class of moon we see in the outer solar system around the giant planets called the ice moons. So like Europa, Ganymede, Callisto, Enceladus, moons like this that are largely surfaces of water ice. What we've come to realize from direct measurement, though, is that as a class of moon, they probably harbor vast reservoirs of liquid water under those icy surfaces. And it's a statistic that's never really been advertised as widely as it should have. We've known about water on this moon, Europa, for almost 20 years now, but nobody's really pushed the statistic of how much liquid water there is on Europa. There's about 2 times the amount of liquid water on Europa as there is on planet Earth. Okay? So if you're actually an unbiased alien astrobiologist coming to the solar system, you probably start on somewhere like Europa rather than planet Earth if you just thought life was going to be water-based and living in a water-rich environment. Anyway, that's chapter 2. Chapter 3, Titan. I felt bad including 3 solar system objects, but I could not include Titan because it's so weird. It is alien. It's the alien interloper in our own solar system. But it's got everything we think might be important to life. Liquid, it doesn't have to be H2O, it happens to be ethane and methane. Has organic chemicals in abundance. It's like a petrochemical refinery gone crazy. Okay? And it has energy flowing through it, sunlight coming through it, this kind of thing. And the reason I'm so fascinated by Titan is because if there is any kind of life on Titan, it's probably going to be so different to our preconceptions. And that's when I'm at my happiest, is when I see our preconceptions about what the universe is like being challenged. Okay? Now, I said this is the summary, so I'm not going to dawdle you. Exoplanets. We're discovering exoplanets, planets beyond orbiting distance stars, in literal abundance now, thousands. Our views of them are also becoming substantially more detailed. This is an image, not of an exoplanet itself, but what may be what we call a protoplanetary system, something on the route to forming a mature solar system, but not there yet. It's an image of a dusty disk around the star HL Tauri. Okay? And what you're seeing there in the inset is an image with the new ALMA radio interferometer that produces images of stunning spatial resolution. You can see incredibly fine details there. The width of that almost looks like an old-fashioned vinyl record. The width of that is about 2 times the extent of Neptune's orbit in our own solar system. So you're really seeing down to the scale of perhaps individual planetary orbits here. And those gaps you can see that are like the grooves in the vinyl record are gaps in the dust disk that we think have been cleared by the gravitational effects of planets growing as we think they did in our own solar system in its earliest phases. Okay? It's quite a classical image of an exoplanet, but it contains so much detail. And seeing is really believing. In the summary, I just wanted to give you an image that really shows you an awful lot of science. Without having to understand the physics, you can see this solar nebula forming, planets forming in it. The last one, I could not do it because so many people wanted it. It inspires the public so much. Is SETI. Okay? And SETI is a great subject to discuss from a scientific perspective because it polarizes opinion. Many scientists are vehemently anti-SETI. They don't think it should deserve public funding, etc. And I found it really interesting to confront those arguments. My own view of SETI has changed a bit. It's softened, I should say. But Joe gave me 45 minutes. If I try and do every chapter equally, well, I've already blown some of my 45 minutes, so I'm going to have less than 9 minutes per subject, and that just ain't going to work. Okay? It's also a question of priorities from another perspective. Okay? All science projects are limited by funding. And the only way I could really get that across in the book was I gave you, the reader, $4 billion. And through the book, when I tell you about a particular venture, a particular project, I try and give you a ballpark estimate of how much it costs. Okay? It's also useful because at the end I have to front up and tell you what my stakes are, right? Because there's no point posing the problem to you and not answering it myself. Now, to put that in perspective, the NASA planetary science budget is about $1.2 billion per year. So that $4 billion is about 4 years of funding. You can focus on whichever projects you think show the greatest promise of success. It's also, I think, rightly thought-provoking to remember that it also corresponds to 1 day of annual global defense spending. Okay. Now, I'm not trying to give you a particularly political motivated message, but I do think it's a healthy social exercise to ask where the products of our own effort, our tax dollars, go to. Okay? And so that gives you the scale of those $4 billion. Now, let's get down to business. So I don't want to skip the details. The first object I would like to look at is Enceladus. Okay? I even prepared a finding chart for you to locate it. You basically find Saturn, head right. Okay? Or left. It depends kind of when you are. Now, Enceladus typically is about 11th magnitude. And I thought this would be a great opportunity. I've never observed it directly. Has anybody here ever observed Enceladus directly? Or imaged it? Okay. I mean, certainly it's within the grasp of the astro imagers, I think. I'm not sure whether it's within the grasp. I haven't done the calculation of whether you can do it with the 32 inch. But, you know, what of course I do to work this out is I just asked myself when was it discovered, and then at that period in history I asked what was the biggest telescope. That kind of tells me what's roughly possible. Okay? So I haven't done that piece of research yet. Now, I don't know if you can quite read it. There's Enceladus, just about 2 times the radius of the rings from Saturn itself. Now, it's still quite suspicious, and it's something we're going to come to, that it happens to sit in the middle, while the inner ring is this large diffuse feature called the E ring. That's not by chance. Now, Enceladus. Oh, thank you, my lightsaber. So there we go, there's Enceladus, just hiding there. Okay. Now, Enceladus is an ice moon. When you look at the surface, I'll show you an image in a moment, you're seeing H2O in its solid form, and large amounts of it. But it's a tiny moon. It's about 400 kilometers across. It's not exactly circular. It's around roughly 400 by 500 kilometers in its diameter dimensions. Okay, and so there it is shown with respect to our moon and of course planet Earth. interesting thing is, if you scale planet Earth and Enceladus, the sizes of the bodies, by their relative amounts of liquid water they contain, Enceladus would be much bigger, contains an appreciable fraction of Earth's reserves of liquid water. Now, there's another, this is just a nice image that gives us a sense of perspective as well. This is taken from Cassini, the current NASA probe orbiting Saturn. So this is an image of the illuminated crescent of Enceladus. And here's the other big Saturnian moon, Titan, right behind it. Okay, nice moment to capture the two of these. There's a Cassini mosaic of one hemisphere, the illuminated hemisphere of Enceladus. One thing you notice here, well, let me tell you a few basic things. All of that you're seeing there is H2O at about minus 180 degrees Celsius, okay, 75 degrees Kelvin, about minus 190 actually. And when I looked at this image after this summer, I looked at after the Pluto mission again. And having seen the images of Pluto, what do you notice about the surface of Enceladus? In terms of its age, it's both young and old at the same time. What you see is, and this is why astronomy is a great subject for informing the general public, here you see quite heavily cratered terrain with overlapping multiple craters. It's billions of years old. But then you see regions that are essentially crater-free, and that means in terms of ages from cratering counts, that particular part of the surface is less than 50 million years old, which compared to the age of the solar system, 4.5 billion years, is the absolute blink of an eye. So this is, if you like, baby soft skin. But you ask yourself, what's the process that's fueling that cryogeology, where water plays the same role, geological role on Enceladus as normal rock does on Earth? Okay, what's fueling that activity? Well, we think it's tidal energy. Okay, now without getting into the details of tidal energy, it simply arises because moons like Enceladus around Saturn or Europa around Jupiter are what are called tidally locked. Okay? But they're in these resonance orbits, but because there are multiple moons, they're kept in these resonance orbits. And that means that each orbit, Enceladus in particular, is ever so slightly squashed and squeezed as it completes one orbit around Saturn. And that squashing and squeezing deposits energy in the center of Enceladus in the form of friction. Rock layers simply rubbing against each other, just like those squash and racquetball players amongst us. When you warm up the ball at the start of a game, you'll first of all throw it on the ground, and you give it a good kick around and then whack it against the wall a few times. You're heating up the ball with friction. Okay? That same process heats up the interior of Enceladus. Also the same process that heats up the interior of moons like Europa that give us these vast reservoirs of liquid water. But there's a reason why I'm telling you about Enceladus and not Europa. Now Europa, that reservoir of liquid water, is trapped under an ice sheet, maybe somewhere between 10 and 30 kilometers thick, and it's staying there. And then somebody goes down with a very, very deep drill. Okay? The reason why I'm telling you about Enceladus is because you can access that ocean free. This is one of the most impactful Cassini images I've ever seen taken. This is an image of Enceladus, and this is sunlight reflecting off material pouring out at the south pole of Enceladus. In terms of relative location, we can hit what's called the tiger stripes, these grey longitudinal cracks. It turns out they are fissures, and to the best of our understanding, you're seeing liquid water escaping from the under ice surface and then vaporizing as it hits the vacuum of space. Okay? Now we've taken spectra of this, we've even sampled it physically. It's real H2O. Okay? Good plain old stuff. It also contains something else. This information comes from an instrument on procedure called the INMS, the Ion and Neutral Mass Spectrometer. It's simply a device that weighs, in atomic mass units, individual molecules. Okay? So you're familiar with individual molecules formula. Let's say methane, CH4, one carbon atom and 4 hydrogen atoms. If you add all those together, you get an atom, a molecule, I should say, that is made up of 16 atomic mass units, 12 for carbon and 4 for hydrogen. So if you look at that in a mass spectrometer, you will see a signature with a spike of 12. Other formulae, other molecules give you different molecular weights. And so this mass spectrometer has actually flown on Cassini through these geyser plumes, and it shows us there's methane, there's water vapor, simple organic chemicals, there's carbon monoxide there, and then complex organic chemicals. The reason why you can't be more specific is because there may be more than one type of molecule that has the same molecular weight, and also because the actual ability of the mass spectrometer to resolve different molecules of mass is quite limited. So the individual spikes that you would see from different molecules get broadened out and overlapped, so you can't quite tell which is which anymore. But it tells us that Enceladus, to the best of our knowledge, has all three basic ingredients for life. Even with our biased Earth perspective, it's got water, it's got organic materials, organic chemicals, this is carbon-bearing chemicals, and it's got energy in the form of this tidal energy that's flowing from the center to the surface of Enceladus. Now, that's all well and good. All we want to do is actually get some of that. That's the whole point in Enceladus. We don't have to go to Europa and drill through an ice sheet. We just have to, it's rather audacious, fly through that plume, capture some of the material, and return it to Earth. Earth is the best laboratory you're ever going to have. You can take the samples that you get, and you can think up any experiment you want and design it there on the spot and actually apply it to the data. With a robotic mission, you have to think up your science package, make it very small, finalize the design 20 years before your probe flies, and then send it 10 years into the outer solar system, okay? You can't change anything. So sample return is really the name of the game. Very controversial as well. Okay, I'll explain a little bit about that. And so what would you name this venture? Well, the imaginative among you would call it the low-cost Enceladus sample return. That's the real name. There's a brand of deck sealant in Britain. It's called Bronze Seal. Put on the deck, it's sealed against the rain. The advertising slogan is, it does what it says on the tin. Okay? That's the low-cost Enceladus sample return mission. It's partly advertising, because this has got to go through NASA committees and funding agencies, this kind of thing. So the first thing you want to emphasize is low cost. Okay? This will fit within your budget. Okay? Now, the other great thing about this mission is that it uses an awful lot of proven technology. It's not pie in the sky. What you actually see here is the classic deep space probe architecture of a high-gain antenna for communicating with Earth, a spacecraft bus, and then a little deployable flap here to capture the material. Okay? Now, some of you might be aware, some of you might not be. We've actually flown 2 missions like this before, but not to Saturn, but to pass through comet tails in the inner solar system. There's the NASA Stardust mission and the Japanese Space Agency Hayabusa probe. Both of those have captured cometary material and returned it to Earth. Okay? Consequently, really just like the Andromeda strain. Okay? And that's the controversy of sample return as well. You don't know what you're bringing home on your shoes. Okay? And you want to be very careful how you clean them before you come back into the house. But the way you do this, the main focus of the mission, so it's just like, part of it's just like Cassini. You're going to send a probe out to Saturn. The other part of the mission is just like Stardust and Hayabusa. You're going to fly the probe through the plumes multiple times and collect samples of the plume material, the geyser material, the water, the organic chemicals, and anything else that's come along for the ride. That's the idea. If there is biologically active material, I could say cells, I could say microbes, maybe that's a biased view, in that ocean water that gets vented into space, you're going to pick up some sign of it. That's the idea, that's the motivation for the $1 billion investment. Now, this is actually what the aerogel looks like. This is the aerogel array on the Stardust probe. Okay? Aerogel Well, it does what it says on the tin. It's basically a gel that's mostly air. Okay, it's an incredibly low density but structurally sound material, and it captures individual particles by basically slowing them down with impacts, and then they're trapped in the solid structure. And then what you do is you fold your array away, you put it into some hopefully safe sample return container, and you bring it back to Earth. Then you just got to kind of find some way of getting it safely back to the surface. Right? That's the one thing no one's done before. Okay? Here's kind of a schematic of the mission. Now, the route to the outer planets of the solar system is actually well trodden. We first did it with Pioneer 10, then Pioneer 11, then Voyager 1, then Voyager 2, then Galileo, then Cassini. Okay? Getting out to the outer planets is not really the difficult thing. It actually doesn't even take that much time, depending upon the kind of rocket you bolt it to. Okay? It can be as long as 8.5 years if you try this gravitational slingshot method. This is the famous method that was really used to its fullest extent by Voyager 2, that each time you pass a giant planet, or even a minor planet in the solar system, if you coordinate your approach and leaving the planet with sufficient precision, you can steal a little bit of orbital energy from the planet and take it to your spacecraft, and consequently speed up for free. Okay? Or you can be lazy and use NASA's new Space Launch System, which is their new heavy-lift rocket, and basically put a very large booster on top of that. You could, if you want to, get to Saturn in about 2.5 years. Okay? It's all about bucks, right? Do you want to pay for the high-speed train ride, or do you want to go in the Uber taxi? Now, you encounter Saturn, you then need a little bit of propellant left to actually roll down your gravitational hill back to Earth. That's where the problem happens. Okay? When you're back at Earth, you're probably traveling at somewhere between 12 and 16 kilometers per second. Okay? Now that's fast. The Stardust and the Hayabusa probes came back in at somewhere between 4 and 6 kilometers per second. Okay? Now, that energy was lost by essentially breaking in Earth's atmosphere and dumping your kinetic energy in the form of heat by friction, by a heat shield. Now, let's use the factor 5 to 15 kilometers per second. That's 3 times faster. That's 9 times the kinetic energy. That's basically an order of magnitude more energy to lose. It's a very difficult orbital maneuver, so that's the one unknown. How much does it cost? That's what I told you about. Well, these guys have actually applied for what's called the NASA Discovery class mission, which is cost capped at about $500 million, which amazed me because when I started writing the book 2 years ago, their price tag was about $2.5 billion. Okay? So I wonder what they've cut off. What doesn't get included in the price tag for that $500 million is the launch system, the rocket. Okay, that can be anywhere upwards between $100 and $300 million, maybe even more if you go for a new type of rocket. The other thing they can't afford to pay for themselves is the battery. Okay? You've got to run that system out at the distance of Saturn. And there's not much solar power left. You need a huge solar array to capture enough energy to create enough electricity to run your probe. And solar panels don't work well when you're flying through geysers either. And so the typical route that's been taken by NASA deep space missions is to use, essentially, a nuclear battery. To use the physical heat produced by decaying radioactive plutonium to generate electricity via a thermoelectric generator. They come by the very fancy name of a radioisotope thermoelectric generator. It's basically a plutonium battery. The plutonium is not producing fission or anything like that, or a chain reaction, but the natural decays in the highly radioactive material make it very hot. And it stays hot for about 30 to 40 years. And that heat is what's generating electricity. Yeah, the problem is NASA's running out of plutonium. Okay, about 10, 15 years ago, you may not know this, the USA finally decided it had enough nuclear weapons. It had enough plutonium. So it turned off the very messy and polluting set of nuclear reactors that produced plutonium via uranium fission. Okay, that was why the US has had a dirty reactor program for the last 50 years, because it's a great source of plutonium. But they decided they had enough, they turned it off, and so NASA's left with a few blocks of plutonium, right? And each one of those will give you a space mission. In NASA, it's just called the problem, okay? And so, where the battery comes from to power that, those radioisotopes, thermoelectric generators, they'll set you back about $300 million, okay? So it's a bit more than a lithium ion, right? But it will last for about 30 years on one charge. So that's where it is. That's where I'm focusing at the moment. We've applied for money. The typical success rate means that you might have to apply, even with a good idea, about 4 or 5 times and wait about 10 years before you finally get money. So, don't hold your breath. But that's probably my #1 pick. We're not getting a tantalizing glimpse of life. That's the important thing to say there. This is actually your chance to physically get a sample back on Earth and do very detailed biochemical experiments. Okay. So that's why it's my #1 pick. How long have I been talking for?
Half an hour.
Okay, great. Because I've just learned a realistic price tag is about $2.5 billion, right? So that half an hour, I've just learned about 2.5 billion. But I've got 1.5 billion left. Okay? So that's the rest of the talk. What am I going to spend it on? Some of you may have seen this news story over the summer. This was the discovery of a planet orbiting a star about 1,400 light years away from Earth. It's the 452nd planet to be confirmed by the Kepler Space Observatory. That's why it has the name there. Kepler 452a is the name we give the star. The first planet to be detected is B, C, and D, and E, and G. And it made the news because some people decided it was the most Earth-like planet that we had discovered yet. Okay? Now, the reason why we think it's Earth-like is we know what the star's like. It's a G2 dwarf star, rather like our own sun. It takes 385 days to orbit its parent star. Now, this is the great thing about studying our own solar system. Kepler's laws apply to our solar system and every other solar system that's out there. You can't change them. And so if you have a star that's about the same mass as our own sun, and if it takes about the same amount of time to go around it, it must have the same distance from its sun as we do. Otherwise it wouldn't satisfy Kepler's law. So that means the amount of energy it receives on a given day is just like a typical day here. You could stand on the surface and warm yourself on the surface if it had an atmosphere, right? These are things that we don't know now. I've given you the total summary of what we know about this planet. There's one other thing we know. It's 1.6 times the radius of planet Earth as well, so about 4 times the volume. Okay. Now, on the basis of that, this is where I start to get a bit skeptical of the NASA press machine. Okay. Nobody observed these nice clouds and continents and liquid water on the surface. Okay, that's all an extrapolation. All we did was we found a planet that's 1.6 times the size of Earth in an orbit that's similar to Earth's orbit around the sun, similar to our own sun. Okay? And I was reading this, and I read the paper that came out that day, and I was reading it, and I thought, and then I read the press release, and I thought, this is all a bit optimistic. And as often happens, I got a call from CFAX, or I forget CBC, calling up, and luckily I got caller ID, and I thought, they best not put me on the radio for this one, because I thought they were really pushing this too far, calling it Earth's twin and making all of these extrapolations. Okay, so I respectfully declined. I need to cut the phone for that one. I've been doing a lot of interviews for the New Horizons, Pro, Pluto, this kind of thing. So I decided to duck that one. Now, I don't want to give you the whole technical spiel on Kepler and how it finds planets. The basic idea is that just like Venus transits in front of our own sun as viewed from Earth, certain planets that orbit around distant stars appear to pass in front of their own stars as viewed from Earth, and it makes a tiny dip in the light we see. But a repetitive dip that will happen once per orbital period. And so even though it may be of low significance and difficult to detect, if you keep looking, you will see in this system, once every 385 days, it will dip by about 1 part in 10,000 in the light from that star. That's how we know that there are planets going around. I told you that these were challenging accessible light sky objects. So here's your findings chart for Kepler 452. Okay. So there's the field that Kepler observed. The mission in its primary sense is now no longer continuing. It lasted about 4 years. But every second of every hour of every day for 4 years, Kepler would observe that field, repeatedly taking the brightnesses of stars and just plotting them as a function of time, looking in each and every star for a rhythmic dip that was an indicator of a planet passing in front of its parent star. And that pattern of squares you can see there is the shape the detectors would make on the sky. It has this incredibly large field of view with digital camera. It's a very precise, it's very stable. So there you can see it basically between Cygnus and Lyra. You've got Vega up there, and other notable night sky objects. Now the actual star is about 13th magnitude. It's not an easy object, but once again, if you're an astro imager, I think it's well within your reach. And that's just the Palomar Observatory All-Sky Survey image that I took off the web there. So that's just a publicly available image. And I took the right ascension and declination of the star, and that's it. So that's Kepler 452. Sometimes, with astronomy, professional or amateur, and you look at objects in the night sky, you have to use your imagination a little bit to tell you what's really going on, because Kepler 452 is just a point of light. But we know with certainty there is a planet orbiting that star. It's about 4 times the size of Earth, and it has, some Earth-like conditions on there. Let me give you one slide that just gives you the overall impression of what Kepler has done for our knowledge of planets and why it's an exciting time. On the left-hand that was the state of play in, let me see, 2014 of every planet we knew of that was not detected by the Kepler Space Observatory. They're detected by different methods, some using Earth-based transit observations, some using this famous stellar radial velocity, Doppler wobble technique, if you like. And there is a few hundred planets on there. This is what Kepler's done over its 4-year mission lifetime. Went from a few hundred to a few thousand planets. Also, the properties of the planets we're able to detect became quite different. Now, there's a little theoretical trick here. You use the term these planet masses in the planet radii. I don't want to go into that. But the important thing is that Kepler, because of its exquisite precision, is able to routinely detect planets about the size of Earth. So don't hold your breath anymore. We're detecting Earth-like planets. The question is, what are we going to do with them? And as I said, I want to be very specific and tell you about how we're going to find life on these planets. Well, the key is you have to think about the relationship between, let's say, life on Earth and Earth's atmosphere. That's the key. Now I'm going to, right now, biologically alter the composition of Earth's atmosphere. All right? No, I just did it. Okay? I'm not going to repeat it because I'll start to hyperventilate. Okay? I brought in oxygen and I used it by a metabolic reaction in my cells that produced energy, carbon dioxide, and water, okay, to break down sugars. Now, if I was a plant, I'd be doing something slightly more interesting. I'd actually be taking in CO2, which is rather abundant, non-biological gas in our atmosphere, and I'd be expelling oxygen. And oxygen's an interesting gas because the only way we know of producing oxygen, molecular oxygen, is biologically, via reactions such as photosynthesis. It doesn't stay around long either. If we were to turn off all life on Earth right now, that oxygen would slowly but surely all react with everything on the surface of the Earth and start to rust things. Now, it would last about 2 million years, which seems a long time to you and me, but that's not actually a long time in the history of the universe. So oxygen would be used up unless there was a continual source of it. So gases like oxygen in our own atmosphere are called atmospheric biomarkers. It's a fancy way of saying a fingerprint, okay, a clue. The challenge, though, is how on earth would we look at the atmosphere of an exoplanet? Well, I wanted to show you stuff that's within our reach, and it is within our reach. Here's the basic idea. It's called now you see it, now you don't. When you see a planet in a transiting system like I've shown you, sometimes the planet will be off to the side or in front of the star, and sometimes it will be hidden behind it in eclipse. One of those frames, you see the light from the star and the planet, and in the other, in eclipse, you just see the light from the star. Now, it's very simple, but it's difficult to achieve in practice. You just take one away from the other, and you're left with just the spectrum of the planet. The challenge is noise and photometric stability. How well can you characterize the light in each of those frames, and how stable is your instrument in recording that light between successive exposures? That's the challenge, okay? The idea is very simple. Now, here's a planetary spectrum. It's our planetary spectrum. This is Earth. I wish I could tell you more about it. Maybe A is my favorite one. Earth is the optical spectrum of Earth viewed from Earthshine. It's this wonderful experiment. You don't take a spectrum of planet Earth, you take a spectrum of Earthshine on the moon. And that is basically the light from the sun that's bounced off planet Earth, back off the moon and back to us. And it's a way of determining what the Earth looks like in terms of when viewed from space. I've actually done that experiment at the Sierra Observatory, where I worked in Chile about 10 years ago. And the other two frames come from satellite observations, but you see Earth's atmosphere with its what are called spectroscopically active molecular compounds there. So ozone, molecular oxygen, water, carbon dioxide, methane, all of these absorb light in some wavelengths. The reason why you don't see the gas that makes up 80% of our atmosphere, nitrogen, is because it's not spectroscopically active. In the form of molecular nitrogen, it just doesn't absorb light. It doesn't have any absorption bands. Okay? So the goal is to take that simple A minus B method for an exoplanet, and you hope you're going to see something like that. This is what you get. Everything I wanted to show you is techniques we can actually do right now. So this is a Hubble Space Telescope spectrum of trillions of exoplanets due to it's basically, it's like Kepler 452 in that it's a super Earth. It's a planet that's maybe about 4 times the mass of Earth. Okay. Now we know it has an atmosphere because we can, from very detailed secondary measurements, I'm not going to actually tell you about. But this is the interesting thing. Those black lines are the spectrum. It doesn't kind of look like the nice big absorption bands you see in our own planet. It looks featureless. And the current explanation is because it's cloudy. Okay? So we have a problem of observing through the clouds. Exoplanet atmospheric spectroscopists have the problem of when the planet is cloudy, because none of the light goes through the planet then, or through the atmosphere, it just bounces off the surface, and it looks featureless. Okay? We don't know yet whether they were unlucky with this super Earth, or whether cloudy planets are the norm. We might say it's more like looking at Venus than looking at Earth in that sense. I'm getting to the end of my talk. What am I going to spend my remaining few $1 billion on? This. Now I'm going to talk over this as we go on. If you want to look at an object close to the sun on a sunny day, you may be driving along or you're looking at your friend off in the distance in the sunset. What do? You just put your hand in the way, you block the sun out, right? And it reduces the glare and you can see objects at lower contrast. This is the same idea. You take a space telescope, maybe the James Webb Space Telescope or another orbiting facility, and well, you need to put a hand in the way out in space to block the light from the distant star, and hopefully you'll be able to see the planets going around it. This is the idea. So what they're going to do is they take this occulter, this star shape, they deploy it in space, they move it across the glare of the parent star, and then the hope is that it suppresses the light from the parent star enough that you can see the planets passing around the edge. The planets themselves aren't actually that faint. They're well within the range of even our modern telescopes, if you could only just suppress the light from the star. Okay? Now this is an engineering model. It looks really rather flimsy, a little bit embarrassing at this stage, but this is an engineering model of how you might deploy it. What I wanted to ask you was, I can't pause it. Okay? I'm assuming you guys are actually better at optics than I am. Do you know why the star shape is not circular but has those strange petal shapes? It actually has a long history. It's because of what's called the spot of Arago. Now, Arago was an 18th century, I think, Portuguese scientist. About the same time as Huygens, the first sort of era when we understood diffraction. If you block out a star with a purely circular aperture, you will see a small amount of light from the star will always diffract around the edge and give you a coherent peak of light, albeit small, in the middle. And because the star is about 10 billion times brighter than the planet, that will still outshine the planet. Okay? And that spot of light caused by coherent diffraction in the center is called the spot of Arago. But if you no longer have a circle, but this quite deliberately designed petal pattern, it breaks up that central peak of diffraction light in the center, and means that you don't get what is called constructive interference, you get destructive interference. The spot goes away, the glare goes away. So it's a very, I love the design of it. Okay. I thought that was pretty cheap. I thought I could spend maybe $1 billion on that. It turns out the chap doing this has just asked for $3 billion from NASA. Right? I have to say, unless he can make it cheaper, he hasn't got a hope in hell. Right? Because for $3 billion, you could fly to Saturn and back and bring back, nice frozen crystals of the underside of Enceladus. Okay? Whereas this doesn't even buy you a telescope, it just buys you a shape you put in front of the telescope. Now, I am running out of time, and I don't want to keep you guys too late. This, of course, is SETI. Okay? Now, just to put it into perspective, I've just spent around about $4 billion, okay, between those two projects. Now, SETI, I think, had a very welcome windfall this summer that a private philanthropic organization called the Breakthrough Foundation decided that, yes, SETI is a dream. Maybe it's the impossible dream, but it's one that this particular Russian Silicon Valley entrepreneur wanted to fund. So he gave SETI $100 million. Okay? In terms of the $4 billion I've been talking about, it's a drop in the ocean, it's small change. Okay? So if I had any small change, I'm actually quite, I would support that kind of activity because it's his money, he can spend it how he wants. Okay? And, despite the criticisms you can level at SETI, the main one is, if you don't hear anything, what have you learned? What have you got for your $100 million bucks? Okay? When you explore the solar system in, say, a more incremental, physically motivated way, you might not find life. You learn fundamental facts about the makeup of the planets, things like that. Okay? The main criticism you level at SETI is, if you don't hear anything, what have you gained? Where have you got to? Right? The aliens aren't broadcasting on that particular frequency, or maybe they're using light waves instead of radio waves. You don't know. Okay? But still, relative to 4 billion, I'm not unhappy to see 100 million bit of SETI. I'm just going to read you this last bit because everyone wants to know why I've got Bill Clinton as my last slide. Okay? The reason I've got Bill Clinton as my last slide is because he's the only president of the United States who have actively commented on astrobiology and talked about it, okay, in detail. This was on the occasion of the NASA report on the Martian meteorite, Allen Hills 84001. You have to go all the way back to 1995, okay? And the NASA team had just published a paper in Science on possible relic biological activity in the Martian meteorite, Allen Hills 84001, okay? The scientists were fairly measured. It was a good paper, it's still a good paper to read, okay? It's a very readable paper. But then the NASA press machine kind of took over, and it ended up on the White House lawn with Bill Clinton saying these following words about discovery. Okay? It speaks of the possibility of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered. Its implications are as far-reaching, awe-inspiring as can be imagined. Even as it promises answers to some of our oldest questions, it poses still others even more fundamental. For those of you like me who remember Clinton, it's classic Clinton. It's inspiring, it's uplifting, I feel energized, and it contains no information whatsoever. It's the art of political oratory, it's masterful. And this is my point at which I end. Everybody talks in astrobiology about research answering our most fundamental questions without ever telling you what those questions are. Right? And I tell my class at the end of each year, this is one of my last slides I give them, what that means is your questions that you can formulate are just as fundamental as anything that any highly paid scientist can. They might be different in their technical nature, but they can still get to the heart of the matter. And so that's kind of where I stop now, and let you guys ask your questions to show me how fundamental they are. Thank you.
Questions? There has to be a question somewhere here.
Given that we've been doing like docking in orbit since Gemini, is it just the cost of the braking maneuvers that keeps us from doing a bunch of series of brakes to get us synced up to the space station?
Yeah, that would be a great way to do sample return, is not bring it back to Earth, okay? But it just costs propellant, okay? So, and as you know, any fuel you want to use for braking at the end of your mission has to be carried all the way throughout the mission. And that kind of magnifies all the way through the size of the rocket needed to get to low Earth orbit, to get up to Saturn, this kind of thing. It's a law of diminishing returns. And so people have always looked at aerobraking as it's free, okay, a way of dumping energy, well, within the cost of the heat shield, right? But yeah, so it would just cost you in mass. You have to take the fuel required to generate the braking energy to reduce your velocity with you all the way through. That's the real challenge, I think.
My favorite is still Europa. So, is
Yeah.
it just the cost?
It's just the ice.
Yeah, the cost of breaking through the ice?
Yeah, and, you know.
Or techniques for breaking through the ice?
Well, it's been an exciting time, the last 3 years, because there's been 3 projects in Antarctica trying to drill through to what are called Antarctic subglacial lakes. So this is underneath the ice sheet, so between 1 and 2 kilometers under the ice sheet. We know from radar studies that there are bodies of liquid that have been separated from the outside world for anything between 250,000 years and 2 million years. So as ecosystems, they're really interesting. Now, it kind of sums up national identities. The British tried it, had a glorious failure. The Russians tried it in a crude and dirty way that everybody else criticized because they didn't have sterilized equipment. And the Americans kind of had an all singing, all dancing, but ultimately successful venture. Okay? And so they did the Lake Willows. Okay? And it's tough. Because the toughest thing about drilling a hole through 2 or a kilometer of ice is it refreezes. Because effectively you're melting the ice as you go through it, and then it refreezes as you're drilling. And so you get this very limited window over which you can actually keep the borehole open. That was the trouble on Earth. I mean, and it's just the scale on Europa. We don't yet even know how thick the ice sheet is. The guesses we have are just guesses. The reason is that although the Galileo space probe had a magnetometer that could detect the conductivity of the water under the surface, the liquid water under the surface, it didn't carry a radar instrument. And so it wasn't able to tell how the surface of Europa buckles and bends through each orbit. And that helps you understand how thick the ice sheet is. And that we just don't know yet. So let's say it's 30 kilometers of ice. That's daunting. Truly daunting to get through, especially when Enceladus gives it to you for free. Any questions?
I was just wondering about some of the previous missions that have gone up to things like comets and asteroids and that sort of thing. With the science that you've done with those programs, has there anything been discovered? Have you been following some of those missions?
They're both daunted by the fact they've got very few particles. They're really dealing with individual particle traces. And as far as I'm aware, and this is, I do have limited knowledge here, we didn't learn a great deal more than we learned from just doing, say, spectroscopy of cometary tails in terms of understanding what's in them. But that's more my lack of detailed knowledge than anything else. Yeah. Questions?
A lot of the talks have been on individual projects, but the number for SETI at the end, 100 million, how many years would that actually fund the research for them?
Yeah. I don't know. I'm thinking because these guys are operating on just a complete shoestring, right? Because the passion of these guys to keep the project going has been quite inspirational. Despite what you may think of the project overall, I think they'll probably get between 5 and 10 years out of it, because the main amount of money is just buying time on Arecibo, I think. It's not salaries or this kind of thing. It's not like, when you look at the cost of building a Mars mission, like the new Mars rover, the substantial cost of the mission is actually paying people at the Jet Propulsion to build it, and to keep all those engineers working, as well as the cost of getting out there, etc. So I think their day-to-day costs are quite low. It's actually buying into Arecibo. So
Will that save Arecibo? I understand it was to be shut down or sacrificed or whatever.
You know as much as I do on that project. Yeah.
So that 100 million could be.
Yeah, I don't know what role that might play, but, yeah. I mean, all I know is that 100 million people get $100 million, get to all the friends, because suddenly, well, no, this guy wanted to announce the $100 million of funding, so as well as Dan Worthington, the PI of SETI, they had Mark Rees, the UK Astronomer Royal, they had Stephen Hawking, and they had Jeff Marcy, the guy who discovered an awful lot of exoplanets by the stellar radio velocity. So, you know, people turn up and you've got $100 million on the table. So.
Thank you very much. Any more questions? We can adjourn to the coffee and cookies.
I should get Bill to.
Thank you very much.